How you guys doing? Are you enjoying the sessions? In my session, I would love to talk about ZK and security. So we'll keep this session a little more interactive. So I just want to know how many of you guys are directly or indirectly involved into security, or have previously or currently working with a proving system or something like that? Anyone? That's great. There are some people. It's good to know. All right. So the ZK verifiers. The security of ZK verifiers is a very less explored topic right now because there are different implementations, like protocols have their own version of implementations, which I think are secure based on understanding research papers or having their own understanding of the design or the construct, right? But in that case, there are, like, these implementations tend to suppose different bugs, different implementation bugs, right? So these bugs, which I'm going to explain, are coming from my practical experience of working with different zero-knowledge protocols and auditing or reviewing their verifiers and the proving systems, right? So in the past, I worked and audited the Linux verifier, and right now I'm working at ZKsync. So I'm getting the chance to work with the ZKsync's proving system and the verifiers, right? Cool. A quick introduction. Who am I? Pretty weird name. It's called as Tejaswa Rastogi. Please do not pronounce it. You can just call me Razor. It's super simple and right. Who am I? I'm a security engineer and researcher at ZKsync. My roles and responsibilities involve working around anything and everything in security, like conducting audits for the code base, researching about new attack vectors or the current existing schemes or new constructs, helping the team build some tools or something like that, right? Love cats. You will see that. Okay, so we'll explore practical bugs or the real life bugs that may exist while constructing these kind of verifiers, right? So I tried to generalize these bugs around stocks. These could be anywhere, like these are not limited to just snarks or just stocks. These are pretty generalized and totally depends upon how you take these and implement them, right? So let's talk about the starting point, right? For the proving system, like Plonk, right? You must have heard about the Plonkish proving system, right? So they require something called as trusted setup. So what is a trusted setup? Basically, those who don't know, it's just like a step where you find a random element in a field, right? You raise some powers of it, right? Here you can see a tau, right? It's called as tau. It's a random field element that we find, of course, belonging to the field. We raise some powers of it, right? Tau 1, 2, 3. Now you might ask, like, why we are raising the powers and how many powers we are supposed to raise, right? That totally depends upon the polynomial we want to work with, or the business we want to satisfy with the polynomial, right? So every polynomial may require a different set of the powers of tau, right? Here you can see like g raised to tau. So g is nothing like just a generator, right? So we are encoding the powers of tau with the generator, right? Now, tau raised to 2, and so on, right? So this depends upon the polynomial, as we talked about. different polynomial, different requirement for the powers of tau, right? And now what is the need of these powers of tau, right? So when a prover wants to commit to a polynomial, right? So how you commit to a polynomial? Let's assume like this phi of x is a polynomial, which can be represented as in the form of coefficients, the summation of the product of coefficients and the variable raised to exponents, right? That's basic algebra, right? Basic maths. That's how a polynomial looks like. So if a prover wants to commit to this polynomial, he or she just want to raise or just want to evaluate the polynomial at tau, right? Now the basic requirement of this string, we call it SRS, structure reference string, the powers of tau. The basic requirement or the most requirement of the powers of tau, that after raising the powers or after finding the powers, you're supposed to delete tau. You're supposed to like waste or discard tau. That's why it's called as toxic waste. Why? We'll come to that point, right? So let's consider first that we have discarded tau, right? So if we have to commit to this polynomial, again, back to the basic maths, how you will find g raised to phi of tau. It's simple. Now we don't have tau, right? But we do have the powers of tau, right? So what we'll do, we'll again do the same math, like because phi of 0, tau of 1, tau of 0, phi 1, tau 1, phi 2, tau 2, depends upon the degree of polynomial. Let's say you have a polynomial of degree 2, right? So just feed in all the values here. Phi 0, tau 0, we calculated. Phi 1, tau 1, we raised the power of tau, tau 1 we have. Similarly, other terms we have. So without having the knowledge of tau, we can still compute this term, which is exactly what we needed, right? So we can say we can commit to a polynomial without even knowing what is tau. Now, imagine if we do not discard tau and the attacker gets the excess of this tau, right? What he or she can do without even knowing the polynomial or for any different polynomial, right? Okay, now let's try to go back. Like, okay, we calculated these strings, right? So let's say in the start we knew that our polynomial was of degree 2. So we calculated the powers raised to 2, tau raised to 2. And after that, we discarded tau. Why? Because we can commit to the polynomial by just having the knowledge of tau, right? Powers of tau, right? Now imagine the attacker gets access to tau, right? Now, does he or she need the powers of tau? Definitely not. What if it's a degree 3 polynomial, right? The attacker knows tau. He or she can directly go ahead and raise the power of tau to 3, right? Before that, was it possible? No, right? Because nobody knows tau. So you cannot raise the power of tau raised to 3 because if your polynomial changes, if you try to forge the proofs, if you try to trick the system, you cannot because you don't have the knowledge of tau. So from all this conversation, we can conclude that tau is the most important thing. And once you are done with the powers of tau, you're supposed to delete it, discard it. Now imagine the powers of tau was calculated or computed by one single entity, right? That creates like issues of trust, right? Because you're dependent on a single entity to be responsible of discarding the tau. If does not, there are chances of the tau getting leaked or being used for malicious activities. So what's the solution? what if these powers of tau are being calculated in an MPC fashion? Now, what is MPC? Multi-party computation, right? Like 5 of us are calculating the powers of tau, right? So with that, even if one of the 5 people remains like a good actor, you cannot cheat the system, right? Because you need all of the 5 people going rogue to cheat or trick the system, right? So with that, what we concluded? Single party SRS? No. What do you want? MPC? Good. Right? Cool. Another cool thing is static calls, right? We all know about static calls, right? Pretty basic thing in the EVM structure, right? So when we write verifiers, right, we usually write them in Yule. Why Yule? To save computation cost, because we know Salty keeps or maintains many housekeeping, of course, right? Like many security checks are placed in by default, right? So if you are 100% sure what you are doing, you can just write it in Yule and place the required checks based on your need, right? So most of the verifiers, or all the verifiers, are usually written in Yule to save gas cost or computation cost. So a simple static call looks like this. The first parameter is gas, the address, and the argument and the return offsets, right? A simple structure. What is 8? 8 is the address of the precompile, EC pairing, right? Everyone knows about the precompiles, right? We have a certain set of precompiles, efficient computation. So address 8 is a precompile called as EC pairing, right? So for the EC pairing, we require certain kind of parameters, right, to pass in. A simple structure of that EC pairing computation looks like this, right? Storing all the values at a specific offsets in the memory, and then calling the static call with all the memory offsets, the complete region of memory, and just wanted to check the result, right? Okay, going back. Yes. If I do my static call like this, what is the issue? Can anyone guess? If I just want to keep my static call like this, you just saw the next slide, you might have guessed it already. Basically, static call provides a return status, right? That whether the call was successful or not, right? If we are not checking the return status of static call, it may happen the static call was failed, right? But since you're progressing in your code and you're not checking the return status, it can happen that the result of this static call was false or invalid or failure or anything, but you still consider this as valid, right? And moved ahead in your code, right? Imagine the result of EC pairing, right? Imagine the most important part of the verifier, EC pairing, failed, right? But it still proceeded because you're not checking the return status. Okay, so what we can do now? Any guesses what we have to do to improve this? Come on, now you can say that. Of course, check the return status, right? So now we can check the return status and now it's fine, right? Any guesses? Is it fine now? We did what you said. No, basically, because we are just checking the return status of the call, right? The return status can be true, but the pairing can fail, right? What we are checking here is the status of the call, whether the call was successful or not. Are we checking the result of the pairing? No. So even if we are checking the return status of the static call, the pairing is still failing. So what we have to do, we have to check the yielded value from the pairing, right? So the first thing we do, we will check whether the call was successful. If yes, even if the call was successful, now we have to check what is the yielded result of the pairing, because the pairing could have resulted false, right? The call was successful, the pairing result could have been false as well, right? Now we have to check both the status yields true, right? Now we can consider that the static call are working fine or the implementation is fine. Now imagine you're making a verifier like this and you miss these checks, right? What an attacker can do? An attacker can pass any arbitrary data or the final pairings, right? For the final opening proofs, right? Any garbage data, right? It will pass because you have not included a check, right? So what we have concluded from this thing, ignoring return status, bad thing. Validating return status, good thing. We are becoming good hackers, right? Moving on to some range checks, right? So if you have worked with a verifier or a proving system, right, the transcript or the proof elements contain many components, right, many elements based on the construct, right, based on the proving system which are needed, right? Consider some of the examples. Proof L at zeta, proof R at zeta, these are the evaluations at a point zeta, right? Now, how many of you know about these precompiled EC mull, EC add? Right? We know? We don't know? Come on. So EC add and EC mull are precompiles given to us for efficient addition and multiplication on elliptic curve, right? These are precompiles. So EC mull, like as we know, requires 3 points. The three things. First, the point on the curve, the x and y coordinates, and the scalar with which you want to point addition, which you want to do the point addition with the point, or scalar multiplication with the point, right? Like 1, 2, like generate a point raised to 2, right? So it will do the EC multiplication. Now the problem with EC mull is that, yes, it checks the points are on the curve and they are in the field, but for the scalar, it does not check. So what you can do, so this is the curve that it follows, the EC mull, y square x cubed plus 3, alt bn 128, the curve it follows. This is the field with p, denoted by p. So now imagine if I do proof L at zeta as proof L at zeta plus R mod. R mod is the field, length of the field, right? So what an attacker can leverage with this knowledge or this construct, since you're not checking or not restricting the elements to be in the field, attacker can take the advantage and overflow the element, right, out of the field. It will still be valid because S plus R mod is still S, right? Like if you do 5 plus 7 mod 7, it will be 7. 7? Basic maths. 5, right? The same example. You can overflow these elements, take them out of the field since you're not checking or not the implementation is checking. An attacker can take advantage and provide the same value in a different format, right? And if you don't have enough checks, there is a high chance two things can happen. Either your implementation will not understand what's going on and will simply revert, or it may happen that an attacker may find a way to use the same proof in two different ways, same value in two different ways, and try to forge the proofs, right? So pretty basic thing, but it can do a lot of damage. Same goes for public inputs. They are supposed to be constrained in the field, right? Another thing, same. These are also proof elements. Proof L, X, proof L, Y are like some of the proof elements, right? So for these elements, at some point in the verifier design, you're supposed to use ECAD. These values are supposed to go through ECAD computation. So now we know that, like, okay, so in the previous slide, I told you, okay, ECAD does the checks, right, itself. So why do we need to add more checks? Right, you're absolutely right. Yes, it does, but what if these computations are happening like after a lot of computation in the verifier, right? You're still wasting gas in the computation. You could have implemented checks in the beginning and just revert it, right? So not like you can say a bug or something, but some checks that you can add. So what we learn from this, if you have no field, you will get a goal, right? And if you have field checks, you're a good person, good boy. Like Ronaldo? No? Cool. Back to maths. Hope you guys don't hate maths. So this is the bug I found in Linus implementation. Lagrange polynomial evaluation in zeta. Okay. So in the implementation, like I will not try to explain you the whole verifying methodology. We'll just stick to basic maths, right? So just believe on my words, right? So in the implementations, at some point after doing computation, we have to find some Lagrange evaluations, right? At some point zeta, right? So this is an efficient formula. Like if you can, like I will just read it. Like Li at zeta is equal to omega raised to I divided by n multiplied by zeta raised to n minus 1 divided by zeta minus omega raised to I, so, right? Like a long formula. It's just an efficient form to calculate the polynomial evaluation. Now what is omega? What is omega? Like root of unity. So what is root of unity? It's just nothing but a simple term. Like if you raise that term to a power, it will yield 1. So if it's a fourth root of unity, omega raised to 4 will be 1. If it's fifth root of unity, omega raised to 5 equals to 1. So imagine if zeta is a challenge, right? If zeta comes out to be a root at unity, right? So what will be the value? 1. 1 minus 1, 0. The whole term will be 0. So in that case, what you will calculate will be a different or a wrong value as compared to which was supposed to be, right? So you're not supposed, and one more thing, the research paper, the Plonk paper, tells you to calculate Lagrange evaluation like this. But you're not supposed to do it. So now you have two options. If the value of zeta comes out to be a root of unity, you're supposed to make a check to revert it because you cannot proceed with that. Your verifier cannot deal the vanishing polynomial of 0. That's one case. Second thing, just change the formula. Do it in a like primary fashion way, like we used to do in the like algebra classes, right? So this is the intended formula. If you calculate the value like this, you will get the right results, and your verifier will work just as fine, right? So this was there in the Linux implementation. It was fixed, and yeah. Now, if you're reading, so these bugs or this knowledge is also very good for bug hunters, right? If you are hunting on Immunify or any bug hunting platform, or just reviewing the code base of a protocol, right? You can go in and search for these kind of checks, right? What if you get $1 million, right? So what we learned, if no validations for Lagrange evaluation at zeta for the 0, bad. But if you have validations, you're a good person, and you're progressing, and you're a good reviewer, hacker mindset, like a hacker cat, right? Good. Okay, one last thing, right? Like there are many bugs like that I want to discuss about, but the time is short. So I will talk about like this major problem. This is a very big problem in the constructs. It's called as frozen heart. If I'm not wrong, the name is given by Trail of Biz, and they have nice articles here. Sure, you cannot read them, but if you just search frozen heart Trail of Biz, you'll find articles on that. What is frozen heart? Like, before understanding the bug, let's understand why it's even here, right? So, how many of you know about Fiat-Chamy transformations? Great. Do you want to like try in a line what it does? Great answer. Okay, so Fiat-Chamy transformations. So it's basically nothing, just a framework which was designed. So consider interactive proofs, how they're supposed to work, right? Basically, prover got a polynomial, right? We want to commit to the polynomial, right? It will ask verifier, now give me a challenge, right? The verifier will give a challenge, right? And the prover will try to evaluate at that point and send back, right? So what happens here, it involves or it needs interaction. The prover needs to wait for the verifier to give me a challenge, and then I try to evaluate. So basically, to avoid this thing, what was designed and created called SNARKs, means non-interactive argument of knowledge, right? So what was designed, what if we avoid this interaction and still able to do the verification just as is without compromising the security, the cryptographic security of the construct, right? So what was designed, okay, whatever the public inputs are there, like proof elements, whatever the inputs are there, I will just hash all of them down, right? And then try to create the challenges which were needed. Right, absolute right thing, right? If you hash all of the thing down, like in the public transcript, the attacker, like how an attacker will try to forge the proof, because if he's sending some inputs which are getting hashed, the attacker doesn't know what will be the resultant value, right? Now, what if you miss something while hashing the inputs? Let's say there are 10 public inputs in the construct, but you hashed only 9, right? You missed something, you forgot, or maybe you thought it's not necessary to hash them down or hash it down because maybe like anything that you thought like, okay, not needed, not secure enough, something, right? Avoid it, right? The attacker will take advantage of that, right? And will try to find a way to forge a proof by sending malicious public input, but still having the same proof, or modifying the proof. Like, let's say there is a proof, right? I do not know like what proof I have to send or what public input I have to send, but I can put in any random data, right, for the public input, and can figure out my way to find out the right constraints or the right data needed, right? So just giving you a hacker methodology, like it's practical. What I'm sharing right now is the way hackers exploited this bug, or you can probably go ahead and exploit by just checking out implementation, right? This can give you like easily $1 million for sure. Like it's that critical bug. So what you're supposed to do, go ahead and find out implementations, right? Any verifier implementations. And just check whether all the public inputs are being hashed or not. If you find something which is missing, what you're supposed to do, take the construct, right? Take the construct, make a fork of the whole verifier implementation, right? And make an arbitrary public input, right? Any random data. Because you don't know, you're an attacker, right? You're supposed to forge the proof. You're trying to attack the system. Okay, any random public input, right? Send all the public values, right, by your garbage public input to the fork of the verifier, right? And after that, find out where it's reverting. For your convenience, you can avoid the final pairing check so that you're easily able to proceed with certain steps. Find out where it's reverting. Avoid the checks, right? And just take out the values which you have found till that point which you needed, like inverse, like Lagrange evaluations, U, challenge U, something like that. Okay, you got some values which were required initially, which you did not have, right? Now you have all the values by modifying the verifier implementation a little bit, right? Send all those values back in the implementation because you have the correct values, random public input, but you find out the right values after sending to that, right? And then you can verify the proof. It's that simple. And you are $1 million rich, at least. Cool, what we have learned. Missing public values in Fear-Shamir hash computation. Bad. But if you hash all the public inputs, you are good hacker. More. You want more? More bugs? Well, we don't have enough time, so next time. Okay? And what if you forget me after the event and no discussions with me, nothing, no interactions? Bad kitty, right? But if you stay in touch with me and follow me on LinkedIn and Twitter, you're a good cat. Right? So that's it, and I hope you have liked it and learned something, and I conclude my presentation.
Thank you. So we don't have time for questions, but remember to follow Razor on Twitter. So it's Razor_tweet.
It's Razor, yeah.
Yeah, okay.
Thank you. Any questions?
Very insightful. Sorry?
Any questions?
I think we don't have time for questions.
Okay, thank you.
Maybe, sorry, but remember to follow.